In this video, we're going to learn how to calculate compound interest. Now, there are several ways to calculate compounded interest. You can compound it once a year, and this is very similar to a formula we talked about in a previous lesson, where you start with a principal starting amount. You do 1 plus either your growth or decay factor. In this case, since we're compounding, it's going to be a growth factor, raised to t some time period that you want to grow over. The rate you put in should be typically an annual rate, and the time will be in years to match the annual time period. So, if you wanted to break that compounding up over a year, we'll still use the same rate that's an annual rate, and the time will still be in years. But let's say you want to break up that rate over 12 months. Well, you do is just divide r by 12, and the number of times a year by 12 as well. So if that was 5 years, you have 12 months per 5 years. So 60 months would go there, and you break up your rates over that time period. Now, if we keep doing more and more times a year, we should make more and more money, and I'll go over what that looks like in a future example. If you do it an infinite number of times, meaning n is a huge number, then we approach this formula: a is equal to the principal times e to the rate times time, where e is a very particular number whenever n is huge for the expression 1 plus 1 over n to the nth power. Now, I know this is 1 plus r over n to the nth, and that's what e to the r is equal to, but I'm going to show you where that initial number comes from, and then you can repeat this process for like e squared and e to the third, and you can see that it's a same pattern every time for very large values of n. This, by the way, is called a limit, and it just means use a very large value for n, and that's what this is equal to. So let's go over what the value of e should be. So I wrote down a little table. I said n is 1, 5, 10, 1,000, million, billion. I'm going to use a very big value for n. I'm going to notice a pattern happen for this expression. So I wrote out what 1 over n is, and then I added 1 to it to get 1 plus 1 over n. And we're going to calculate what this expression is together right now. So I want to figure out when n is 1, what is 1 plus 1 over n to the n power? So I'm just going to take 2 and raise it to the first power, which will just give me 2. But then when I do 1.2 to the fifth power, I'm going to need a calculator to help me. So 1.2 to the fifth power. That gives me 2.48832. Now let's do 1.1 to the 10th. Still getting bigger. So 2.59374246. But it didn't go up as much as it did before, so it kind of gives you the idea this is going to start to flatten out, or at least go up very slowly. But we'll see. Let's plug in n is 1,000, so we'll have 1.001 to the 1,000th power. So 1.001 to the 1,000th power, which gives me 2.716923932. But we'll do it again with a million this time. So this 1.1 plus 1 over n is now 1.000001 raised to the 1 millionth power, which will be 2.718280469. And you're going to start seeing a pattern. There's now similar digits past the decimal point that they have in common. So the bigger we make this n value, the closer we get to the actual value of e, which if I now use a billion, which at this point I'm just going to use 10 to the negative ninth when I do 1 over n, or 10 to the ninth power for 1 billion to make this go by a little bit smoother. So I'll have 1 plus 10 to the negative ninth raised to the 10 to the ninth power. That's a billion. And 10 to the negative ninth is at 0.0000001. 0.0000001. When I plug that in, I get 2.718281827. And you see they have all these decimals in common, so I can at least say that E is approximately 2.71828. So that's where that number comes from. It comes from this natural transition from each of these compoundings until we want to do an infinite number of them in a year. But now let's use that. And if you ever want to calculate what E is with your calculator, E to a power, right above the ln key, if you do second ln, you get E to a power. If I do E to the first, I can get that approximation I just found. And I can do E to any power I want to. So second ln, E squared is this number. So if I plugged in 2 over n here, it should approach that decimal, and so on and so forth. But now let's try this out with an example. So let's find the amount in a compounded account for the given conditions. The principal is $950. The annual interest rate is 6.5%, and it goes over 10 years. So let's see what happens when we only do it once a year versus quarterly, as 4 times a year, monthly, 12 times a year, and then continuously, which is like an infinite number of times in a year. So once a year is going to look like this. A of t will equal 950 times 1 plus 0.6065 to the t power. So A of t will equal 950 times 1.065 to the t power. And if I want to figure out what happens over 10 years, I'll need to plug this into my calculator. So I'll have 950 times 1.065 to the 10th power, and I'll end up with $1,783.28. To $1,783.28. But let's see if we do it quarterly, so 4 times throughout the year. But we'll break up the rate for all those moments. So the function will be A of t will equal 950 times 1 plus 0.065 divided by 4, and then raised to the 4t power, which means that A of t will equal 950 times, to plug that in, 1 plus 0.065 divided by 4 is 1.01625 to the 4t power. So A of 10 would equal 950 times 1.01625 to the 40th power. So when I plug this in, to avoid making any mistakes, I'm going to put 950 times the answer, so second minus symbol, just to carry that over from before, to the 40th power. And that gives me more money than it did before. So the more times you compound in a year, the more money you should make. So let's say we do it monthly, so once a month. Well, that would be A of t equals 950 times 1 plus 0.065 divided by 12 to the 12t power. So that's A of t is equal to 950 times 1 point, let's figure out what that decimal is, 1 plus 0.065 divided by 12, 0.054, and then 1, 6 repeating to the 12t power. And that's going to be dangerous to round in this case, so I'm just going to use the answer situation in this next part. But A of 10 in this case will equal 950 times 1.005417 to the 120th power under 12 times 10. And A of 10 will be 950 times the answer from above, raised to the 120th power, which will be $1,816.57. It's not much more, but you are still getting more money. So this continuous one where it ends 1,000 is probably the maximum you could possibly get from compounding interest. So that will be A of t will equal the principal 950 times e to the rates 0.065 t for the function. So A of 10 will equal 950 times e to the 0.065 times 10, which should be 950 times e to the 0.65 power. And doing this, second ln to the 0.65 power, I get A of 10 is equal to $1,819.76. So you'll see here that the more compoundings you do, the more money you'll get as you go from like quarterly to monthly all the way to continuously. You'll see here you start getting like diminishing returns the more you do. So oftentimes they'll use this formula just to see here's the maximum amount, but if we just do monthly, it'll be a few dollars off, but it's pretty close. And you'll see here with yearly, you're missing out on a good chunk of money, almost what looks like here like $40. So now let's put this into an application. So suppose you won a contest at the start of 5th grade that deposited $3,000 into an account that pays 5% annual interest, compounded continuously. How much will you have in the account when you enter high school 4 years later? So see how much money we make on it from its initial value. So we know it's compounded continuously. So we're going to use this formula. So A of t will equal the principal, which is $3,000, times e to the rate, which is 5%, so 0.05 t. And we know that t, the number of years, is 4 years, because we were from the start of 5th to the start of 9th. So A of 5 will equal 3,000 e to the 0.05 times 4. And 0.05 times 4 should be 0.2, but let's calculate that. 0.2. So A of 5 is 3,000 e to the 0.2 power, which is $3,664. And they want to round it to the nearest dollar, so I won't put the 21 cents. So this will be how much money? So over 4 years, it accrued $600 just sitting there. And that is how you calculate compounded interest.